I would like to mention that if you watch the previous videos where details of carbocation chemistry I have discussed from 1 to part 7, then you will be able to understand all these problems easily. Okay, so let's start. So all these videos you can get in the description box. The playlist link is given there. We have to find the major product formed in the following reaction. Okay. Here we have BF3.OET2. So in presence of this reagent, as this is electron deficient, so the lone pair over oxygen that will be donated to this. So just ignoring the stereochemistry, because without that also we can reach the correct answer. So here we have methyl group, another methyl group here, and now oxygen is attached with OBF3. There will be negative charge over boron and positive charge over oxygen. Now among these two bonds, if we break this, there will be generation of 3-degree carbocation. So that is the driving force. Positive charge will not generate to the other side, it will generate here, see, like this. And oxygen is now neutral, there is negative charge over boron and BF3. Next, the hydrogen which is present here, it will be shifted to the carbocation. And why we are doing so? Because if we do so, now the positive charge that will come just beside oxygen, and that is very stable. So positive charge will now come here, and it is stable because of this lone pair donation from oxygen. So just put all the methyl groups, hydrogen is here, and finally this OB bond will be broken and there will be CO bond generation. So what structure we are getting? There are two 5-membered ring, two methyl groups here, we have another methyl group here, and there is double bond. So the answer that we are reaching is basically option 1. Fine. Now what about the stereochemistry? How we can explain it? Though in this case we do not need it, but what is the explanation behind it? To understand that this structure I will write in a different way, so that we are able to understand what is concave phase and what is convex phase. So here these two methyl groups that are present like this, and this is another methyl group, and as positive charge is here, it is planar. Fine. And remember previous, that is initial structure, oxygen is below the plane, so that is why it will be written as OBF3 and hydrogen is at the upper side. Okay. Now what is the convex phase here? So this phase is basically convex phase, and though two methyl groups are on this side, but still hydrogen will be donated towards this, that is migrated towards this carbon from the upper side, because as this is the convex phase, attack from this side compared to the other side, it is facile. So that is why hydrogen, if it is migrating from this side, now methyl will be below. So that is why here you can see this structure, hydrogen is up, methyl is below the plane. Okay, so this is the explanation. Option 1 is the correct option. Next we have here OH group is present. In presence of H, we are obviously this OH, it will be protonated. So after protonation, it will be OH2, and OH2 it is a good leaving group. So if it is removed, there will be generation of carbocation. So what carbocation we are getting? We are getting this carbocation. Fine. There is cyclopropane ring. Now if I do numbering, basically here the ring will be broken, so that is why numbering is important. 1, 2, 3 and 4. So here 2,4 bond, 2,4 bond will be broken, and there will be generation of a double bond at position 1 and 2 like this. So what we are getting? Triple bond as it is, double bond, then 2 more carbon. So this is 1, this is 2, this is 3, this is 4, and at 4 position, as 2,4 bond broken, there will be positive charge. Now finally in the medium there is Br minus present, so Br minus will attack here. Basically if you can reach up to this point, if you know that CC bond will be broken, so obviously it will be option 3, because in all the other structures there is 3-membered ring. So only option 3 we are getting the correct answer. Okay. So this question, it is dione phenol rearrangement. So what is dione phenol rearrangement? See, this is dione. So there is C double bond O carbonyl and 2 CC bond present. So this type of structure, how it is giving this type of rearrangement, that we will try to see with this general example. So in this example, here what will happen in presence of H plus, first there will be protonation of this OH group. Now depending on this R group, in which case the migrating tendency is high, it will be migrating here, and this CC bond, double bond, that will be shifted. So once it is shifted, we are getting double bond here, positive charge will be here, R group, and finally this hydrogen, this CH bond will be broken, and what we are getting this structure. Now depending if these two R groups are different, depending on the structure, one of them will be migrating. Now here we are having methyl group and R group. Now in one case it is R equal to pH, that is pH and methyl combination. Another one is CO2 ET and methyl combination. Now when it is pH, obviously the migrating capability, if we consider, pH will be migrating. So positive charge will be here, and finally there will be phenol structure generation. So if it is so, that is phenyl will be at meta position with respect to OH, then for structure A, it will be either this one or this one, because 3 and 4 you can cancel. Now when it is Me and CO2 ET, at a first glance it seems that methyl will be migrating because it is more donating. But see, if methyl is migrating, the positive charge that is remaining, there is CO2 ET group, which is not very stable. So that is why here actually methyl will not be migrating. You will not get this structure. CO2 ET will be migrating. So it is just like the previous case, that is when phenyl is migrating, the same thing we are now getting. So this positive charge is more stable because methyl group is here. So that is why CO2 ET will be at meta position with respect to OH. So in both cases it is same style. So option 1, that should be the correct option. In presence of CH3, COCl and AlCl3, so these two reagent, it is basically the reagent of Friedel-Crafts reaction. Okay, so though we do not have any aromatic ring, but if you want to know a detail about Friedel-Crafts, then you can watch the video right now. You can click on the link appearing on the screen. In presence of AlCl3, this Cl will be captured by AlCl3 and there will be generation of AlCl4, because this is Lewis acid, fine, negative charge over aluminium, and there will be generation of CH3CO+. So this is actually the electrophile, C plus and O. Now we have this 8-membered ring where we have 2 double bonds. Now any of these bond, if it is attacking C, then positive charge will be generated to the other carbon, that is which is part of this double bond. So suppose this is 1, 2, 3, 4, 5, 6, 7, 8. So this is 8-membered ring. So once it is so, then it is 8-membered. So suppose it is attached here, COCH3. So positive charge that will be generated at 2 position, 1, 2, 3, 4, 5, 6. At 5, 6 there is a double bond, then 7, then 8. Now this another double bond that is present here, this will be attacking the positive charge at 2 in such a way so that you are getting a ring size which should be stable. So if it is 2-6 bond formation, you are getting 5-membered ring both sides. But if you are thinking why not attack from 5, because if you attack from 5, 2, then you will be getting 4-membered ring on one side, 6-membered ring on the other side. So 6-4 combination and 5-5 combination, 5-5 is better. So that is why here 2-6 bond will be formed. Once it is formed, there will be 5-membered ring on both sides. So this is 2, this is 6, 2 and 6, 3, 4, 5. So 5 position there will be positive charge, and at 1 position we have COCH3 group. This is 1, 8 and 7. So finally there is a presence of AlCl4 minus, which you can think as if it is Cl minus and AlCl3 combination. So this Cl minus now attack at 5. So it is matching with basically 2 5-membered ring. Once you understood it, it is basically option 3, right? So Cl, after attack of Cl, it will be like this. Next question. Major product A and B formed in the following reaction sequence. So first we have this type of OH group at 1 and 2 position. In presence of tosyl chloride 1 equivalent, pyridine, calcium carbonate, first we are getting A. Then we have Me3S plus double bond O. Okay, and there is counter ion I minus. Also there is presence of base, and final product is B. Now what will happen here? In presence of TSCl, whenever we have any OH group, suppose if I am writing ROH, it will be converted to ROTS. Now the question is whether it will be, that is, which OH will be attacked. See, if we make the OTS in this CH2H, that is a primary alcohol, then what will happen? CC bond migration is possible, and you will get, that is, ring size will increase. Now ring size increase, that you can see in option 1 and option 4. And if you make the OTS in this OH, now this oxygen lone pair will attack. It will be formation of 3-member ring. In that case, these two are fine. But here, rather than generation of this 3-member ring, 7, that is ring size increase, that is favored. So that is why OTS will be formed in this OH. So what we are getting? 2 methyl group, stereochemistry, it doesn't matter. So OH, and here we have CH2 OTS. Now if we make, that is, break this oxygen hydrogen bond, so it will be shifted here, right, and OTS will be removed. So basically removal of H and OTS, pyridine is there, which can, that is, it can capture this side product. So there will be increase of ring. Right now it is 6, but finally it will be 7-membered. Okay, so suppose if it is 1, 2, 3, 4, 5, 6, 7. So now there is formation of, this is 3, double bond, CO double bond here, and then we have 1, this is 2. So 2-7 bond broken, and this is 7-member ring. Okay, so if you just think about the carbonyl, one side there is 1 CH2, another side there are 2 CH2. So if you look at the option here, we have 2 CH2 on side and 1 CH2 on the other side. So basically it is the same structure. So option 1 or option 4, where ring size is increased, any of this one will be correct. So if this is the structure of A, next what will happen? In presence of this 3-methyl, then sulfur plus, double bond O minus. Now in presence of NH, any of these 3-methyl group, there will be removal of proton. So ultimately you will be getting 1 CH2 minus, then 2 more CH3. We have, sorry, it is sulfur. This is plus, and there is double. Okay, let me the structure properly. So this is positive and there is I minus. Now this is basically sulfur halide. Now what will happen with this sulfur halide? First we will try to see how it is reacting with a compound like this. Suppose we have any heteroatom with 2 R groups or same groups. So how it is reacting with this C double bond X, that we will see first. Okay, there is, forgot to mention this. So this is basically, here I have given this reaction. It is pinacol-pinacolone type of reaction, though it is slightly different. It is not, we have not provided any H plus directly, but TSCl is there. So whatever is pinacol-pinacolone rearrangement is basically formation of a good leaving group from OH. So when you have H plus, there is formation of OH2 plus, and what will happen? This OH, if I am writing this OH like this, and there is positive charge here, 2 methyl group. So this CH bond will be broken, one of the methyl group will be migrating. So this side you are getting Me, then CO, and other side there are 3 methyl group, which is basically this structure, pinacolone. So here also the mechanism is same. That is how from the given substrate you can reach A. So in our case it is formation of OTS, but whatever it is, mechanism is similar. So that is mentioned here. It is based on pinacol-pinacolone rearrangement, which is involving carbocation intermediate. So until what point we have reached? We have reached at this point. So this is sulfur halide. Okay. So this sulfur halide, it will react with this C double bond X. How it is reacting? In general, if we see, It is like this. So suppose this is any C double bond O or any other heteroatom. This is C negative. So this C negative is attacking here. There is negative charge generation. And finally this O minus, because in our case it is O minus. So it will attack this CH2. And there is sulfur on the other side with 2 methyl group and double bond. So this will be now removed. So this is the whole group. It will be removed in the form of dimethyl sulfoxide. And finally what we are getting? We are getting this type of ring, 3-member ring with 2 R groups. So in our case also, as we have already chosen these two as the structure of A, so there will be cyclopropanation. So based on that, this will be cancelled because it is not matching. So here we have this type of 3-member ring. So that is why this is the correct option. Correct order of rate of solvolysis 80% ethanol, 25 degrees centigrade. Solvolysis means what? When you are doing substitution, where solvent molecule is acting as nucleophile. So here 80% ethanol, so ETO minus, that will be the nucleophile. But actual point is, as it is asking correct order of rate of solvolysis, so rate will increase when the stability of carbocation, that will be maximum. So basically the question is asking in which case maximum, you have to find the order of stability of carbocation, that's it. Because once you know the order of stability of carbocation, you can understand the rate of solvolysis. It is directly related to carbocation stability. So if we remove these Br groups, then positive charge will be generated here, SN1 mechanism. Now this positive charge, it is true that it cannot attain planarity, because according to the structure of these three, there is some similarity, you cannot attain planarity, right? But planarity is important. But from that point of view, you cannot, you will not be able to understand which is maximum stable. But what we have to see, if we look at the structure of this ring, structure, that is ring in C, that is basically largest. So larger is the ring size. According to ring size, C is max, then A, and it is minimum in case of B. So CAB. So when there is, that is larger is the ring size, more flexibility the carbocation can achieve. Though it cannot attain planarity, but it can move towards planarity based on this. Because of this, larger is the ring size, flexibility will increase. So CAB, this should be the order, that is option 4. Major product A and B. Look at the first reagent, iodine NaHCO3. So here what will happen, this is basically iodolactonization. Look at the final structure, lactone, that is cyclic ester is formed, and for that we have used iodine and NaHCO3 at the first reagent. Second reagent is base. So what will happen here, iodine, there is CC double bond. So this type of, I am writing here as below the plane, you can also do it the other one. Ring size is 1, 2, 3, 4, okay, it is fine. We have CH2CO2H, but basic medium, so I will write it here as O minus. Now this O minus, it will attack in such a way so that you are getting a 5-member ring. Because if you look at the structure, in all cases it is 5-member ring. Even if structure is not given 5-member ring, it is better, because if you attack at the other position, it will be 4-member ring, which is not stable. So that is why this attack will be actually happen. This CI bond will be broken. So what we are getting, 7-member ring as it is. There is formation of, CH2O, and this is below the plane, right? So on the basis of this, you can choose, that is below the plane, right? So you can choose this one, that is option 1 or option 2. Next, what will happen, at this position we have H. So this iodine, as there is presence of base, so any of these two hydrogen, because if you already selected these two, here the position of CC double bond here, that means this hydrogen, that can also be removed. But which one will be removed? Obviously this one, because if you remove this H and I, you will be getting double bond at this position, which is alpha beta unsaturated ketone, which is more stable. It can take part in resonance. So that is why this alpha beta unsaturated this structure that should be preferred. Fine. So option 2 is the correct option. Again, correct order, that is stability related problem, correct order of stability of the following carbocation. Now all these carbocation, if you consider 1 degree, 2 degree, 3 degree, all are basically 3 degree. So on the basis of that, you cannot do anything. Next, in case of A, there is no resonance possible, which is there is no double bond, and also the heteroatom oxygen, it is not close to positive charge. So here it is not possible. But in case of B, here this type of rearrangement is possible, and once it is done, now this is the newly generated carbocation. So this type of allylic rearrangement is possible. And in case of C, here Plassard effect is coming from this oxygen because it is just beside this positive charge. So if you compare A, obviously it is the least stable, but between B and C you have to give priority to this Plassard effect of oxygen. So that is the maximum stable, it should be C, after that B, and then it is A, that is option 4. Okay. Major product of the following reaction. Here we have 6-member ring and a 4-member ring. But as you have H plus and there is oxygen, so this oxygen will be obviously protonated. Once it is protonated, positive charge, 6-member ring, and there is a 4-member ring. Now this CC bond, if it is breaking, there will be formation of 6-member ring as it is, and there will be formation of a 5-member ring. Okay, so let me do the numbering. 1, 2, 3, 4, 5. So here 2-5 bond broken, 1-5 bond that is formed, 4, 3, 2. Now at sorry, it is here. Now oxygen is neutral, so this is OH. But as we have broken these 2-5 bond, this bond is broken, so obviously there will be positive charge at this position. Next, what will happen? There will be this OH bond, it will be broken, and there will be C double bond O. Now when there is C double bond O, this CC bond, it will be attacking 2. So here what bond? This bond is now broken, and at this position there will be generation of C double bond O. So 5-member ring, and there is one, basically it is not one, if I am, that is, suppose this position if you consider, it will be now connected to this 2 position. So there will be another 5-member ring, and if you maintain the original numbering, it is 2, 3, 4, 5, and at one position now there is C double bond O. So it is matching with option 3. Sorry, not option 3, it is option 4, because see, where the new this pyrocarbon is present, the CO is adjacent to it. Okay, so be very careful, it is not option 3, it is option 4. We have this H plus and oxygen, so obviously this oxygen will be protonated, and suppose for simplicity I am writing this group as R. Oxygen protonated, positive charge. Okay. Now if it is so, now if we break this bond, there will be generation of positive charge, which is 3 degree. So this is 1, 2, 3 and 4. R group, and there is O and H. Positive charge is here. Now if we break this C oxygen hydrogen bond, there will be C double bond O, but in that case we have to break 1, 2, 3, 4. We have to break this 2, 3 bond, and it will come here. That means now there is formation of, so let me draw this 4-member ring first. So this is 1, this is 2, then 1-3 bond formed, so this is 3, and at 2 position there will be basically positive charge, but as we are breaking OH bond and directly we are forming this C double bond O, so that is why final structure it should be like this. You can also, that is, if I do not step jump, it will be like this, that is formation of 3. So there is positive charge as if, so this OH bond will be broken, there will be C double bond O. But directly also you can draw this, and it is matching with, see, between option 1 and 2, be very careful. Here, if you consider these two alkyl groups, it just beside, adjacent to it, carbonyl is present, but here carbonyl is far. So option 2 is the correct option, right? Measure product A and B in the following reaction sequence. First, we have a CC double bond and reagent NBS. Look at the condition. It is aqueous condition, polar condition, also basic. Now NBS, if it is non-polar or H nu is mentioned, then you can do allylic bromination, because allylic bromination is also possible in this molecule. But as this is polar medium, it will not be like this. Basically, it will be simple. Normally, what we do, if you have bromine reagent, this type of bromination we do. So same thing will happen, because the medium is not polar. And for simplicity, I am writing here R group, which is above the plane. So bromination, that will be below the plane. Okay. Now as in the medium you have HO minus present, so it will attack from the upper side, and you will get, now bromine is below the plane, OH is here, and there is this R group, large group, basic medium. So that is why this OH, if I now write it as, so it will attack here, Br will be removed. So finally what we are getting? We are getting, this is above the plane, and here we have this large group. So it is matching with any of these two. Next we have Me2CuLi. This is the structure of A. Me2CuLi, it is basically the source of methyl minus. Now methyl minus, it will attack from below the plane. So ultimately you will be getting OH above the plane and methyl below the plane. That means among these two options, now this is not correct. Option 1 should be the correct option. Structure of B is this. Again, dione phenol rearrangement. So in this case, just look, that is, focus on this part. So if I simply draw this part only, here we have a methyl group, another methyl group above the plane, and we have ring structure, but I am not going into the details of it because that is not required. And that part is also intact. If you look at the options, this part there is no change. Now as it is dione phenol rearrangement, final structure will be phenol. So if it is phenol, then option D or option B, any of these will be correct. Now among these two groups, obviously this will be migrating at this position, that is meta with respect to C double bond O, because this part is, there is no change. And once it is so don't draw the full structure, it is simply wastage of time. So positive charge will be generated here, methyl is here, positive charge, then ring structure as it is. So here we have hydrogen, so that the CH bond will be broken. So finally we will get CC double bond. But important point is the 2-methyl, its positions like this. So this should not be correct. Option B should be the correct option. Now this is very simple. Even if you do not consider the stereochemistry, you can solve this problem. CC double bond is present, so there will be bromination first. Positive charge is there. Now in presence of MEOH, there will be attack either from this side or this side. Suppose this is 1, this is 2. So if you consider attack 1, then obviously as if it is, though free carbocation, even if it is not formed, but as if you are attacking the OMe with at this carbocation. But if you consider attack 2, then as if bromine is here, positive charge is here. Now among these two, obviously this is more stable because it can be stabilized by this lone pair of oxygen. So you can eliminate this option, and methoxy, that will be attacking at this position. So that means beside oxygen there will be OMe group, and that you can find only in option 2, not in any other options, right? So this is the correct option. benzene ring, then we have another ring attached and there is CC double bond. Now in presence of metachloro-part benzoic acid, there will be formation of, there will be epoxidation. Fine. Now we have BF3. So after formation of these, the lone pair of oxygen, this type of problem, remember the first problem of today's video, same type of problem we have seen, O plus and negative. Now two possibilities are there, which side you will broken. If you break this, the positive charge is at this position, which is benzylic position, right? And OBF3 as it is. Now obviously you have to give it preference rather than breaking the other bond, because here this carbocation is more stable. And finally OB bond will be broken and there will be, sorry, one step is left. So this hydrogen, it will be migrating here. So you will get now positive charge here, oxygen, BF3 negative, this bond will be broken and there will be C double bond O. So it is matching with this option 4. Okay, so that's all we have in this video. Thank you for listening.